Hey everyone, welcome back and let's write some more neat code today. So today let's solve the problem max area of an island. This is actually very similar to another problem that we have solved called number of islands. It's pretty much the same general algorithm, but we're returning a slightly different result. Rather than counting the number of islands, we're actually going through every island and figuring out which one of them has the max area, and then we're going to return the max area of any of these islands. So the general idea is the same. We're given a 2D grid where zeros represent water, as you can see they're blue, and ones represent land. And of course, an island is going to be, consecutive one values that are connected either horizontally, right, like from the left and right side, or vertically, so up and down. Two cells that are connected diagonally don't really count. So, if I add one here, if this was a 1, it would still, basically this and this are not connected. They're not an island. They're separately an island. This is a separate island. This is a separate island. This is a separate island. And this is a separate island. So there's really two parts to this algorithm. First, you need to be able to get the area of any given island. And you can do that with your graph algorithm of choice. I prefer doing it with the DFS, depth first search. So understanding depth first search is a prerequisite for this problem. And the good thing is, if you do have a good understanding of DFS, then this problem is pretty easy. All you really have to do is kind of understand how DFS fits into the context of this problem. And in this case, it's actually pretty simple. So I'll be walking through DFS and then walking through how we can apply that to this algorithm. So running DFS on an island, such as this one. So suppose, we start here. We see that it's a 1 value, right? That means it's an island, but is the area of this island just 1 itself, or are there other cells connected to it that are also land? And if there are, we want to run DFS in all directions to basically count how many cells are connected. So the way DFS works is we're going to run DFS above, which we see is out of bounds. So DFS is a recursive algorithm, and since up above we're out of bounds, the DFS is going to return 0, basically telling us that the area of the island in the above direction is 0. Similarly, on the left and right side, it's not out of bounds, but this is water, so it doesn't count as an island. But of course, when we go down, we see we reach a 1, and this 1 has not been visited so far. So again, we reach another 1 value cell, and again, recursively, we're going to run DFS in all 4 directions. So going to the left, which is water, so don't do anything there. Going down, which is also water, don't do anything. We're also going to go up above, actually, even though we've already visited that cell, which is kind of a problem. We don't want to have to go and run DFS recursively on a cell that we've already visited. So the way in DFS to get around that is to have, some kind of data structure. We can call it visit. It's going to be a hash set. So using this hash set, we can kind of mark the positions that we've already visited so that we don't end up revisiting them. That will help us with the time complexity of this problem. And the last direction from here is to go right, where we see that, yes, there's an island. So, we run DFS from this position as well. We look up, nothing there, down, nothing there, left, we've already visited that. Right side is unvisited. So that's the last cell. There's, in all other directions, there's nothing else. So after running DFS on this island, what did we get? What do we want our DFS to return? Well, of course, we want to know the area of every one of these islands, right? That's the only reason we're even running DFS. So DFS from this island should return the value 4 because that's the area of this island. Now it probably makes sense how DFS fits into this problem. Once you get good at writing DFS, DFS becomes trivial. All we have to do is figure out how to apply it to this problem, and it's pretty simple in our case. We're going to run DFS on every single island, and then, keep track of which one of these has the maximum area. As you can see, this one has the maximum area of 6, so we're going to end up returning 6 in this problem. Now, how are we going to run DFS on every single island? The easiest way to do it, since we don't know which cells are 0 and which ones are 1 until we actually look at every single individual cell. That's exactly what we're going to have to do. We're going to start at the top left, look at every single cell. If we see a 1 value, we're going to run DFS on it and figure out the area of that island. If we don't see a 1 value, we're going to skip it. So we're going to have, by the end of it, we're going to have visited every single position and run DFS on every island, so we will know which one is the maximum. The only problem is, what if we run DFS on this position and then we run DFS on this position? Won't we get the same exact area? Won't we run DFS on the same island twice? Well, no, and that's the reason we are using our visit set, because we don't want to run DFS on an island multiple times. So at this point, you can probably see that the time complexity of this problem, since in the worst case, we're really only going to be visiting each cell a constant number of times. It's not going to be, exponential or anything. The time complexity is going to be the size of the entire grid, which we're given is m by n. So in that case, the overall time complexity is going to be m times n. And that's also going to be the memory complexity, because remember, we are having a hash set, which could, in the worst case, contain every single cell in the grid. And of course, DFS is recursive, so there's a call stack associated with it, but this is going to be the memory bottleneck, the hash set. So the time and space complexity is going to be big O m times n. That's enough for us to now jump into the code. Okay, so now let's write the code. If you've seen any of my graph videos, you probably know I like to solve all these problems in a very formulaic way. The first thing I like to do is just get the dimensions of the grid, because usually it comes in handy. So let's get the number of columns and the number of rows in the entire grid. The only other data structure we're going to be needing is the visit hash set, so let's declare that above. And now we want to write our recursive DFS function. I like to just write the DFS inside of our root function, because in that case we won't have to pass in every single parameter. All we are going to be passing in is the position that we're going to be visiting. So RC is going to be the row column that we are running DFS on. We won't have to pass in the visit or the grid itself. And with DFS, we always want to handle the base case first with all recursive functions. One base case is if we go out of bounds. How do we determine that? Well, if row is less than 0 or row is too big, it'll be too big Hey everyone, to the code, the too much code one values, and after we do that, we want to calculate the area of this position, right, of this island. How are we going to do that? Well, the current cell that we're at is going to count as one of the area values, and the other positions we can pretty much run DFS on. The other positions the area values, and the other positions we can pretty much another direction is row -1, another direction will be column +1, and another direction will be column -1. So that's all 4 directions. So each of these DFSs is calculating the area of the remaining portion of the island in each of these 4 directions. Then we're adding all 4 of them up, including the one cell that we are currently visiting right now. And once we've added all those up, all we really need to do is return it, because that's what our DFS is trying to do, just return the area of the island if it hasn't already been visited. So now that we've written our DFS, we've pretty much solved the entire problem. All we really have to do is iterate over the entire grid, which we can do just like this, nested for loops, going through every row, going through every single column in the grid. And actually, let's maintain a single variable. Let's call it area, or you could call it the result. Initially, it's going to be set to 0, right? This is the max area that we're maintaining. Every single time we call our DFS, we want to potentially update the area if it's greater than the current area. So we're going to take the max of the current area and the max of the DFS call that we're going to be doing on the row column pair that we're currently iterating through. And once that is done, we will have the